Okay, now we're going to graph the inverse functions. And so to start here, I graphed the restricted sine function. So this is the sine function on negative pi over 2 to pi over 2. And recall that pi over 2 is about 1.57. So when I invert this, the inputs are going to become my outputs. So if this is 2, 1.57 is about here and here. So the domain here will become the range here. Remember, in inverse functions that gets switched, and then the range of this sine function will become the domain of the inverse sine. So let's go along here and think about what happens. So like this is the point negative pi over 2, negative 1. On the inverse sine function, that will become negative 1, negative pi over 2. Of course, I just wrote that where I need to write my point. Use the screen. So negative 1, negative pi over 2 would be here. And then let's just do a couple other values that we know. So a negative pi over 3, for example, that would be pretty close to the negative 1. Let's see, pi over 3 is about 1.04. So pretty close to negative 1. The sine of pi over 3 is square root of 3 over 2, which is about 0.9. So negative pi over 3, negative 0.9 becomes negative pi 0.9, negative pi over 3. So recall that a function and its inverse are reflections through y equals x. So this part here is reflecting across over here. And we do pi over 6, we get 1/2. Pi over 6 is about 0.52. I already had that one on there because I had started the video earlier and messed up, so I had to start over. So pi over 6, what did I say? Or excuse me, I'm messing up again. I'm going to try not to have to start over this time though. Okay, so at pi over 6, that's about 0.52, we get 1/2 right here. So they almost match up, right? So now we got negative 1/2 and then 0.52. It's still below the y equals x line. It's right there. And then they like get real close together here, and then 0, 0, those points are going to match up on the two graphs. And then we go to pi over 6, 1/2 becomes 1/2 pi over 6. So again, that's like a right here. You can barely even see where it goes. Then at pi over 3.9, now we have 0.9 pi over 3. That's up here. So this point, this is getting reflected over here. Pi over 2, 1 becomes 1 pi over 2. So this green graph, hopefully it looks like the mirror image of sine of x through the line y equals x. This is our inverse function. Okay, so all of the x's and the y's get flipped. So let's do it for a cosine inverse. So we need the restricted cosine function. That goes from 0 to pi. Approximately like that. So 0 to pi, pi is about 3.14, of course. That's going to become the range. I should have had a better graph here. 1, 2, 3. That's going to become the range of my inverse function. And then my domain is going to be negative 1 to 1. Right? That's my original range of my cosine function. So again, this isn't the full cosine function, it's the restricted one, 0 to pi. All right, so let's go through and invert the coordinates. So of course 0, 1 becomes 1, 0, and 1 is approximately right here. And then let's do pi over 4, which would be square root of 2 over 2, which is about 0.7. So that will be 0.7, and then pi over 4 is 0.78. So that's over here. Wait, now I just confused myself. What did I do? So I did pi over 4 square root of 2 over 2 becomes square root of 2 over 2 pi over 4. I need to write it down. So that's about 0.7, and then this is about 0.8. They're almost on the line y equals x. Pi over 4. Oh, 0.7 is here. That's why it's not looking right. 0.7 and then 0.8. I got a point on here that doesn't belong. So here, so we're going from here to here, okay? Y equals x. I should have put different units on here. I would have like labeled these in terms of tenths or something. It would have made this easier. This should go through here. It's more like that. 7. One. 0.7, 0.8, it's about right here. Okay. All right. Then this point, which is pi 0, or pi over 2, 0, excuse me, becomes 0, pi over 2. Pi over 2 is about 1.57, so that comes up like this. Then let's use 3 pi over 4. So this point, my original graph maybe isn't the most accurate either. Okay, 3 pi over 4, comma, square root of 2, negative square root of 2 over 2. 3 pi over 4 is about 2.4. And then negative square root of 2 over 2 is negative 0.7. So if this is negative 1, negative 0.7 maybe about here. And then 2.4 is about here. You know, I'm off, but hopefully you get the idea. You see how this is, this part is, oh, it's off because I have to put a curve this way. This part I've graphed from here to here. This last point is pi negative 1, so there I'll get negative 1 pi. And there, that green one is y equals cosine inverse at x. So again, reflection through y equals x. This part reflects up here. Hopefully you can see that okay. Alright, well let's do the last one, y equals tangent inverse of x. So again, I'll put the tangent function in. We've got asymptotes at pi over 2 and negative pi over 2. Goes through 0, 0. And then at pi over 4, it equals 1. And at negative pi over 4, it equals negative 1. Just use those 3 points. So this domain, negative pi over 2 to pi over 2, will become the range for the inverse tangent function. So the inverse function is going to have horizontal asymptotes instead of vertical. Still going to go through 0, 0. Then this point, pi over 4, 1, will become 1 pi over 4. So it's going to reflect over about right here. What did we say? Pi over 4 is about 0.78. And then this one, negative pi over 4, negative 1, will become negative 1, negative 0.78. So this is going to approach the horizontal asymptote on the upper and the lower. So the green one, like that, and notice that's again the reflection through y equals x. So the green graph is y equals the tangent inverse at x. So the domain is all real numbers. Range is negative 1, or negative pi over 2 to pi over 2, excuse me. Let's write that down. And let's write domain and range for the cosine inverse. So for cosine inverse, domain is negative 1 to 1. So notice that's negative 1 to 1. And then the range is 0 to pi. And then for sine, domain is again negative 1 to 1. This is for sine inverse. Range is negative pi over 2 to pi over 2 from here to here. Okay. Now we're going to look at the inverse properties, and these properties, again, they go back to something we learned about inverse functions back in college algebra. And that is, if you compose two inverse functions, they undo each other, and you should get back to where you started. So if your input was x, you plug it into f inverse, it does its operation, you get an output, you plug that output into f, it does its operations, it's going to spit out x, which is where you started, right? Notice it is undoing, f is undoing the operations of f inverse, and likewise if you reverse the order of composition, f inverse undoes the operations of f, and again you can just get back to x. So that needs to hold for the sine inverse and sine function, pair, cosine inverse, cosine, etc. And these are what the inverse properties say. So we have to be careful about what x is here. This has to do with what the domain and range are of these functions. The domain of the sine inverse function is negative 1 to 1, so this only holds when x is between negative 1 and 1. If you put a 5 in here, sine inverse of 5 is undefined, or 5 is not in the domain, so that won't work. Now if you reverse the order of composition, so the sine function is operating on x, and then you plug that into sine inverse, this is only going to equal x when x is between negative pi over 2 and pi over 2. We can still, if x is not in that range, we can still do the calculation, but sine inverse is going to give us a different answer than what we plugged in. Okay, so that that would be like part D here, which we'll wait and do that in a little bit, but that's what's going to happen with part D. We'll come back to that. Okay, cosine and cosine inverse of x is x. This is similar to the first statement here. X has to be between negative 1 and 1 inclusive in order to evaluate the cosine inverse function. So we have, whoops, that's a plus, that restriction. But then when we reverse the order, cosine inverse has to come from 0 to pi. So this will only equal x if x comes from the interval 0 to pi inclusive. Alright, tangent inverse of x equals x when this time x can be any real number because the domain of the tangent inverse function is all real numbers. So this always works. And here, tangent of inverse at tangent of x will be x. So these will undo each other if x is between negative pi over 2 and pi over 2. Again, because that's the interval you have to choose tangent inverse from as your output. Okay, so let's do some examples. We don't need a calculator for any of these, so let's see what happens. So sine inverse of 0.23. So what people want to do is they look at this and they say, oh, those just cancel and I get 0.23. Okay, well that works fine for this one, but actually let's compare these two. So this is cosine inverse instead, right? Same thing, you say, oh, well those will cancel, they'll undo each other, and I'll just get 2.5. Well, this one, you do get 0.23, but this one is not possible because 2.5 is not in the domain of the cosine inverse function. So you have to not just blindly say that these cancel each other, but think about the value, okay? And that's when the inverse is on the inside. Now if it's tangent, you never have to worry about it because tangent inverse is always defined, so this will just equal 100. Whatever number gives us a tangent that's equal to 100, when we take the tangent of that number, we'll get 100. Alright, so pay attention to the similarities and differences between these three problems. These three have the inverse on the inside. Now B, C, and D have the inverse on the outside of the function, okay? So let's look at these two because they both have 5 pi over 6. These are similar problems, but one has sine inverse and one has cosine inverse. So again, we can't blindly just say these cancel because cosine inverse has to come from a different interval than sine inverse. So what should we do here? Well, cosine inverse comes from the interval 0 to pi. 5 pi over 6 is in that interval, so these will actually cancel and we will get 5 pi over 6. However, sine inverse has to come from negative pi over 2 to pi over 2. So what we want to do is think about, well, if we were at 5 pi over 6, that's over here. Sine is positive, so we're going to take the corresponding angle in quadrant 1 because sine is also positive over here, and that would be pi over 6. Now you can actually evaluate. Sine of 5 pi over 6 is 1/2. Sine inverse, right, that's 1/2. Sine inverse of 1/2 is pi over 6. But even if you didn't know that this was 1/2, you should still be able to figure it out using reference angles, okay? The tangent inverse problems this was very similar to this. 3 pi over 4 is in quadrant 2 for using the unit circle. Well, and that's negative, right? And this is positive. So we need to be, this needs to come from quadrant 1 or quadrant 4. Well, this is quadrant 2, so this does not equal 3 pi over 4. Instead, we're going to get negative pi over 4. That's the correct answer. And I get that because I'm using the same reference angle in quadrant 4. Again, choosing between negative pi over 2 and pi over 2. E. Now, of course, some secant and tangent, those are not inverse functions, so this one's a little different, but maybe kind of separate that from the other 6. We do not need a calculator to do this. Keep in mind that this stands for the number whose tangent is negative 2/5, or if you will, the angle whose tangent is negative 2/5. That number or angle has to come from negative pi over 2 to pi over 2. Since this is negative, I know it needs to be down here. Now this is just the reference angle. This is actually whatever, I'm sorry, I'm lying to you here. This is actually the negative angle. And I'm using a reference angle, but that's going to be the negative of the reference angle. What I was starting to say there, that was wrong. Okay, so the tangent is negative 2/5. We can just use the opposite over hypotenuse. 2/5. I'm going to give this one the negative sign because that's below the x-axis, and this one's positive. Then find r. R would equal the square root of 4 plus 25. So square negative 2 and square 5. So that's the square root of 29. So now I have my triangle with all three of my sides defined. I can find the secant of that. So, you know, if this, I don't need to know what theta is. If I want to call this theta, this stands for the, you know, theta is the angle whose tangent is negative 2/5. In other words, the tangent of theta equals negative 2/5. This is my theta here. I don't need to know what theta is. In fact, I don't want you to use a calculator because that won't give you the radical form of the answer. Secant would be hypotenuse over adjacent. So this is square root of 29 over 5. Right, so I could have put any of the 6 functions here. Once you have all 3 sides, you can calculate that. All right, I've got one more problem to do. This is similar to the last problem, only we don't have the number inside of the inverse function. We just have an expression. And so I'm asking you to write an algebraic expression in x that represents tangent of the cosine inverse of x. Basically do this just like the last problem. Notice I gave you one more thing. Assume x is between 0 and 1. So that's telling you that we're going to be over here in the first quadrant. We're not, if it's negative, we'd be over here. Right? So just draw a triangle. This, remember, this stands for a number or an angle. So if you call it an angle, that might help you keep track of what's going on. So let's let theta equal the cosine inverse at x. So this implies the cosine of theta equals x. And we can think of x as x over 1. So if we call this theta, cosine of theta is x over 1, adjacent over hypotenuse. Right? If this had been between negative 1 and 0, we would have drawn it over here instead, and then theta would be this angle. Once we have this side and this side, we can solve for the remaining side. The radius is 1, right? And let's call this b. Where r is 1. So 1 squared equals x squared plus b squared. 1 squared is, of course, 1. So 1, and I'm going to subtract x squared. 1 minus x squared is b squared. And that implies that b is, and I can see b is positive, so it's the positive square root of 1 minus x squared. So I'm ready to write my final answer. The tangent of theta, or the tangent of cosine inverse at x, right, that's theta, would be opposite over adjacent, square root of 1 minus x squared over x. There's our answer. So whatever this algebraic expression is, think of it as a ratio. Think of the trig ratios. You know, if that had been sine inverse, I would have put x over here. If it had been tangent inverse, it would be opposite over adjacent. So sine inverse would be x and 1. If it were tangent inverse, it would be x would be here and 1 would be here instead. And of course, that would change the radius. Hopefully you get the idea there. Well, let me know if you have any questions, and spend a good amount of time practicing finding the values of the inverse functions, because it takes a little getting used to, because it feels like you're working backwards because you basically have switched the x's and the y's, right? So it takes some getting used to doing that.